So for evaluation of this model, the authors have used a data set which is a combination of the linked data cloud and the data hub. And these two data sets have been merged and they have created a single data set. And for the training of these, they have taken 1,000 triplets from a mixture of 20 ontological languages used. And for the testing, they have created two types. One is they have taken a small portion of the training data set, and another is they have created a synthetic data set by themselves. And for each knowledge graph, they have a set of positive triplets, and they also have a set of invariant triplets. So what they mean by invariant triplets is, for each set of positive triplets, they either replace one of the element by a random element. So when you mean the random element, since you are doing a syntactic normalization of each word, each element in a triplet, you have a positional weight to it. So when you replace it by another random element, you see that the position weight of that element and the weight that is present in the triplet are same. So that is method one, the random permutation, and a random and method two is where this is based on positional replacement. So the training is done in batches of 100 triplets, and if in case the batch size is less, they do a zero padding, wherein the class is other than the yes or no, which in this case is nil. And as explained before, there are these ABC embedding matrices whose length is the vocabularies across the dimensionality of the embeddings. Here, the authors have chosen the dimensionality to be 20, and the evaluation is done based on three factors, which is the precision, recall, and F measure. The next one. So here are the interesting results. So the training dataset is called the OWL, the ontological web language, or OWL centric dataset. That's the training language training dataset used. And we have multiple test datasets. Okay. The linked dataset is one of the datasets that they have created using a different knowledge graphs taken from all the previous studies. And when you see the second one, the all-centric dataset is when you split the training dataset into 90 and 10. And the all-centric test dataset with the superscript of B, it means that the domain in which the dataset is developed is different. So from the training dataset is a different domain, and the test dataset is in a different domain. And the last one is a synthetic dataset which the authors have created algorithms. And here the baseline model is when you take this datasets, the authors are normalizing it using the syntactic normalization process. But if you don't normalize any dataset, it's called the baseline. So they have measured how the model performs against each of the datasets they have. And in this second column, you see that some of the datasets have a superscript of A, which means that in these datasets, they have replaced one of the positional triplet, one of the triplet element with another element of the same position. That's what I described before. So the results are, if you see the accuracy score for the linked dataset, it is higher than the accuracy of the same dataset, which is split between 90 and 10. This is an interesting result, and the authors were not able to find out why it's happened, but they will only say that the linked dataset was somewhat similar when it was constructed from all the KGs to the all-centric dataset. And it's expected that the accuracy should fall when you change the domain of the dataset. And for the synthetic dataset, the accuracy is the lowest because for this all-centric datasets, they prepared in such a way that if you take a multi-hop preparation of these datasets, these datasets were able to be created over a long sequence of multi-hops, whereas a synthetic dataset was cut off from 3 to 4. When I say cut off, it means that they are not able to generate new triplets beyond the third or the fourth hop. That's why there is a huge difference between how the triplets are being formed in this training dataset and the synthetic dataset. And another interesting observation is this. So when they have replaced one of an element in the triplet with a random element, which is denoted by the superscript A. You can see that the recall is the lowest, which is 16. Here, because they are calculating the recall for the classification of the triplet as a no. So it is lowest because the model was classifying all the triplets as yes, because there is a similarity in which the positive and the false negatives were constructed in these data sets, and the model was not able to correctly classify it. But when they train when they take the training data set and do the same replacement of one element with a positional element of the same weight, they were able to increase the accuracy. They were able to see an increase in accuracy. Yeah, next slide. So here are some of the explanations for that. So when they normalize the training data set, they were able to reduce the size from 3033 to 20. And for the non-normalized data set, it is of this size, and it takes huge time to train these. And they see that the normalized data sets occupy much less space and are much faster to process with the model than the non-normalized ones. So when you normalize the data sets, all the words, all the triplets which whose embedding vectors are close are grouped closer. That's why you see a reduction in the dimensionality of normalized versus a non-normalized data set, as you can see here. And the shortcomings of this are, as explained before, when they have tested the model against synthetic data set, the model was not able to perform well. And the model has also performed well against a linked data set, not against a split data set from its own. And they were not able to find out why it happened. And as a future work, the authors want to see how it can be scaled to a synthetic data set, which is more complex. Yeah, these are the references, and thanks for your time.
So how much time do we got for questions?
We got 7 minutes.
7 minutes. Okay. Questions?
In the couch, how does this fit in the couch nomenclature?
System number 4.
Neuro Symbolic, yes.
So you talked about poor runtime performance in terms of training the model. Can you elaborate on that a little bit?
So it was more runtime against a non-normalized data set than against a normalized one, because a non-normalized one has more number of the vocabulary than the normalized one. If you, let's say, for example, similar vocabulary terms like container, bag, in the normalized ones, they are grouped together because the embedding vectors are same. In the non-normalized ones, they both are different and both are unique.
Yeah, I know, but what was the difference between the two in terms of runtime and model size? Did they give any numbers?
No, they did not provide any numbers in that. They just said that the training time is much less for the non-normalized ones, but they did not provide any value for that.
So actually, in the very end of it, they mentioned how the compressed model is, I think, 80 times smaller than the unnormalized one when they compressed it, and then the runtime or the training time was like 40 times less than with the normalized one than unnormal.
But no specific value was given.
No exact concrete.
Okay.